Hi, my name is Marc Castells, and I'm a meteorology master's student who's working on the MarineFlux team at CoAPS. I'm here to tell you what MarineFlux is all about. The main goal of MarineFlux is to make in situ flux observations more findable, accessible, and interoperable. This will be done by creating a web page with a user-friendly interface for finding and downloading flux data and a RESTful API for machine-to-machine queries. Our prototype will cover 1990 to 2020, and we'll use in situ data from SAMOS, which is the FSU Research Vessel Program, ICOADS, which is the International Comprehensive Ocean Atmosphere Dataset, and expeditionary cruises by NOAA's ESRL and PSD. We plan to add more sources in the future, such as moorings and autonomous vessels. The datasets we serve will contain direct flux observations when available, as they are in some of NOAA's ships, and when direct fluxes are not available, fluxes will be estimated using the bulk formulae, which use the ship's measurements of wind speed, air and sea temperature, humidity, and pressure. In this case, these parameters will also be included in the dataset. Other relevant output data from the flux calculations are also included, such as friction velocity, transfer coefficients, and scaling parameters. We also include useful metadata such as the heights of the instruments and which flux algorithm was used and what assumptions were made. What I'm working on right now is the program that runs 3 bulk flux algorithms on ship-based observations from research vessels in the SAMOS program. Much of this work involves examining any available documentation to determine which variables from the ship data correspond to which variables in the flux algorithms, and what differences exist in the variables' definitions. For example, in the wind speed, temperature, and specific humidity at the reference height of 10 meters, the 2 algorithm programs use a different definition of temperature. The MFT outputs potential temperature at 10 meters, while the core algorithm outputs temperature at 10 meters, which can be easily missed when just looking at the variable names, which just use the letter T to denote temperature. To keep track of these differences, I've created a spreadsheet, and the spreadsheet also shows which CF standard name is associated with each of these variables whenever there is one. The standard name uniquely associates the variable to an entry in the CF standard name table. By using this convention in our datasets, we hope to improve the interoperability of our data with existing data and programs. Sean Smith is now using this to coordinate an effort via the Oasis Fair theme team to standardize the terminology the community uses to define air-sea fluxes, the common parameters used to derive those fluxes, and a host of bulk model coefficients, etc. For example, the core algorithm outputs a variable defined as buoyancy flux into ocean. This is one of many variables that does not have a corresponding entry in the CF standard name table, but is important enough to propose adding. So the standard name, downward air surface buoyancy flux, is being proposed by ocean sites. One of the advantages of this coordination is that researchers who are working with NetCDF datasets that were created using the CF convention are able to pull out commonly used variables without having to know what the creator of the dataset decided to name the variable. For example, someone who wanted to plot the buoyancy flux along a ship track would not need to figure out that the NetCDF variable is named HBB, because they can just search for the variable with its standard name attribute set to downward air surface buoyancy flux. Basically, this means that code can be written to be more general purpose rather than specific to certain datasets. Thank you for your time, and if anybody has any questions that I don't get a chance to answer here, or if anyone would like to contribute to the standardizing terminology effort, please feel free to email me at this address.